All right, let's skip the fluff and jump straight into a mystery that could literally save your Cambridge A-level physics grade. Imagine you're sitting there in the exam hall, the clock is ticking down, and boom, you are faced with a massive, high-mark question on dielectric properties. What you write next is either going to secure those top marks or send your grade boundary tumbling.
A dielectric is just a material where current fails to flow. Now, this exact painful learner mistake shows up in mock exams every single year. And let me tell you, it destroys grade boundaries. I mean, it kind of feels intuitive, right? An insulator doesn't conduct, so it's just a failed conductor. But examiners see this over and over, and they are completely unforgiving.
If you write this in your paper, you get absolutely nothing. Zip. 0 marks awarded. Why? Well, because the examiner's looking for a very specific mechanism, not just some vague, passive statement about insulation. They want to know what the material actually does, not just what it fails to do.
Section 1. The common dielectric trap. Why ordinary revision fails.
So, let's really dive in and uncover why treating an insulator as just a failed conductor is a total trap. We've got a clear distinction here between myth and reality. The myth? It's that charges in a dielectric simply cannot move. End of story. But the reality is way more interesting. While charges don't move freely through a dielectric to create a flowing current, they absolutely do respond to an electric field. The bound charges displace, just slightly, from their original positions. The material isn't just sitting there doing nothing. It's actively reacting.
Section 2. Inside a polarized solid, uncovering the microscopic truth.
To snag those top marks, we really need a physical picture of the solid at an atomic level. The absolutely crucial point here is that polarization requires no large-scale current, just an internal rearrangement. When that external field hits the solid, the positive and negative charge centers are pulled in opposite directions. They don't break free, but they stretch and shift. It's like a microscopic game of tug-of-war. This subtle internal displacement is the very heart of dielectric behavior. It's an active mechanism, guys, not a passive failure to conduct.
Okay, here is the exact cause and effect chain you must use in your exams to explain why different dielectrics behave differently. Think of this as your golden framework. Step 1. It starts with an applied external field. Step 2. That causes the internal charge displacement we just talked about. Step 3. That displacement results in a net polarization of the material. And finally, Step 4. This ultimately leads to an altered electrical behavior in the entire system. If you can memorize this chain, you've got the backbone of a perfect answer. Now, you might be wondering, what is the secret examiner clue that transforms this chain into a top band answer? Well, hold that thought for just a second, because first, you need the final pieces of the framework that makes that clue super obvious. We have the cause, now we need to fully understand the effect. Section 3. Altered electrical behavior, the macroscopic consequence. So, what does this microscopic shift actually do to the physical world we can measure? Well, once that internal polarization happens, it fundamentally changes how the electric field behaves inside the material. Because the charges have aligned themselves against the external field, they create their very own opposing internal field. This dictates the total energy storage capacity of the solid. And remember, the strength of this response isn't just random, it heavily depends on the specific material's bonding and atomic structure. Some materials can stretch a ton without breaking, which means they can store massive amounts of energy.
Section 4. Real-world dielectric power, where theory meets application.
You know, examiners absolutely love it when you link these dielectric ideas to practical, real-world electrical systems. Choosing the right dielectric based on its polarization response is absolutely critical for modern tech. In capacitors, the dielectric allows the device to store electrical energy reliably. For high-voltage cables, you desperately need an insulating material that can withstand immensely strong fields without suffering a catastrophic breakdown failure. And in delicate integrated circuits and sensors, dielectrics are used to control electric fields with pinpoint precision. Tying your exam answer to one of these applications, that shows true mastery.
Section 5. Crafting the perfect answer and securing those top boundaries.
All right, let's put on our examiner hats for a minute and construct the ultimate bulletproof answer. These are your 4 anchor prompts. 1. The definition of polarization. 2. The microscopic cause, which is that bound charge displacement. 3. The macroscopic consequence, meaning the altered field and energy storage. And 4. A real-world application, like capacitors. If you could speak through these 4 anchor prompts, in order, you can reconstruct a high-scoring answer no matter how Cambridge decides to phrase the question on the day.
Let's put this to the test.
Go ahead and pause this explainer right now and use those 4 anchor prompts we just learned to predict exactly why this student is losing marks. Think critically about what's missing from their explanation.
Did you catch it? Here is that examiner clue we teased earlier. The top-band answer doesn't just state a fact, it explains the microscopic cause leading directly to the macroscopic consequence. The flawed answer stops at a basic surface-level definition, entirely missing the active mechanism of polarization. But the top-band answer? It hits every single beat of our framework. It shows the applied field causing displacement, resulting in polarization, which ultimately alters the field to store energy in a capacitor. That, my friends, is exactly how you secure full marks.
Okay, so you now know exactly why dielectrics behave the way they do, and you have the qualitative framework to completely crush the descriptive questions. But that leaves a massive high-stakes gap. How do you calculate the exact energy stored by this newly polarized dielectric when you're suddenly faced with a complex data table or a tricky graph?
To get full marks on the quantitative questions, you absolutely must master the mathematical side of this topic. The mandatory next step to secure your grade is jumping into our follow-up data analysis explainer. So head over to that explainer right now and hey, remember to subscribe to Ace the Exams at acetheexams_IGCE to totally excel in your Cambridge exams. So, are you ready to crack the math and lock in that top grade? See you there!